So, all right, so now we have the normal. How do we apply this? Well, what we were trained to do in the old days, because we only had the standard normal tabulated, we would have to reduce everything to the standard normal. It's no big deal. It's very much like standardization that we looked at a couple of weeks ago. And here it is. So if you want to talk about a normal, just a general normal that has a mean mu and a standard deviation sigma, then standardize it. Translate whatever statement you want to make about your x, let's call it x, into a statement about z, where z is your standard normal and their relationship is right there. Subtract the mean, divide by the standard deviation on the x, and that gives you your z, and that's your standardization. Right? So let's look at an example of this use of this idea. So for example, with predictive interval, we know for the standard normal that 95% of the time we can predict. Remember, it's a random variable. We don't know what value the variable is going to take. It's random. That's why it's called a random variable. But we predict that 95% of the time, when you go out and look at a standard normal, it will be between minus 1.96 and plus 1.96. So 95% of the time, we cannot tell you exactly what value you're going to get, but 95% of the time, it'll be in this interval. This is called a predictive interval. We predict that it's going to come between minus 1.96 and 1.96. But you say to me, I don't care about z, I care about x, because I'm measuring things in terms of x. Okay, use the standardization formula. What you say about z, we can translate into statements about x by using the standardization formula, and there it is. So we use it right there. So now let's multiply through by sigma, and let's add mu to everything, and there we've got it. So now this statement about the standard normal gets translated into this statement about your x for general mu and sigma. So what this says is that yes, if we predict x, which is a normal, which is normally distributed with mean mu, standard deviation sigma, we don't know what it's going to be, but 95% of the time, 95% of the time, it will be within plus or minus 2 standard deviations of its mean. That's what this says, right there. Okay? So, for example, let's apply this. If we've got systolic blood pressure, and suppose we're looking at 18 to 74-year-old men in the US. Why am I looking at them? Well, only because I can make the statement that their systolic blood pressure is approximately normally distributed with mean 129 millimeters of mercury and standard deviation of 19.8. So I've got a mu of 129 and a sigma of 19.8, everything being measured in millimeters of mercury. All right? Then, if I want to standardize things, I subtract mu, divide by sigma, and there it is. So my standard variate z is x minus 129 divided by 19.8. So, for example, remember our magic 1.96. So I'm 1.96 on the z scale translates to, multiply both sides by 19.8 and add 129, it translates to x of 167.8. So, for example, in this population, we are going to get a value bigger than 167.8 2.5% of the time. So, for example, if that is an alarm. You can say, all right, if it's bigger than 167.8, this only happens 2.5% of the time. I should try and do something about that for my patient, or for all men in this age group who have blood pressure, systolic blood pressure, above 167.8. Okay, so there it is. With our standard, remember, these were at minus 1.96 and 1.96, so between minus 1.96, so this would be between minus 1.96 and 1.96 is where we get 95% of the area. With our normal, with mean 129, and whatever that standard deviation was, 19.8, these are the upper and lower 95% cutoffs. Okay, so that's how we use this. Okay, and so we can make statements like this. If we choose a person at random from this population, the probability is 0.975 that the person has systolic blood pressure less than 167.8. So we recognize that a systolic blood pressure of greater than 167.8 to be what we might call a rare event, because it only happens 2.5% of the time. We can change that a little bit and ask statements directly on the X scale. So for example, how many have blood pressure above 150 millimeters of mercury? In order to answer that question, we have to go from our X scale of 150, subtract the mean, divide by the standard deviation, to a statement about our standardized Z, and it turns out to be 1.06. So we can ask Stata, what is the area to the left of 1.06? That's the function normal. And it comes back with 0.855. Approximately, 1 minus this, which would be 14.5%. So approximately 14.5% of men in the US between the ages of 18 and 74 have systolic blood pressure above 150 millimeters of mercury. One minor point is I did the arithmetic out here outside of this. I could have asked Stata to do that. I could have said display the normal for 150 minus 129 divided by 19.8, and Stata would have done all that for me in one step, but I thought you'd rather see it in 2 steps. But there we go. So those are the kinds of statements we can make with the normal distribution, with the normal model.